Okay, so let me show you something real quick. But for that, I'll need to switch off the lights. There it is. That is refraction of light. Simple, plain bending of light. Why it happens? Let's understand this in detail. So let's dive in. So, what is refraction of light? Refraction of light simply means bending of light as it passes from one transparent medium to another. Now, most of our lower classes we have learned that light travels in a straight line. But that is true only if the properties of both the mediums through which the light is passing remains the same, or even if it is passing through the same medium and if the properties of that medium are same throughout, then the light ray is going to travel in a straight line. But what if light ray travels from one medium to another where the properties differ? For example, what if the light ray is traveling, as I've shown here, from air into water or water to air, reverse way? In both such cases, you'll find that light ray will not travel in a straight line, but it is going to bend. Now, this bending of light or change in the direction of propagation of light as the light obliquely travels from one medium to another is called as refraction of light. This is one of the most common phenomena which happens around us and which makes us see things in a different way. For example, as I've shown here in the diagram, where you can see a pencil really looks slightly bent when I'm viewing from the side. So you can see the edges are not really matching. So that is because of the refraction of light. Or when you place a coin inside a bowl of water and have look at it from outside, it will look raised from its actual position. This is mainly because our eyes are not made to follow bent path of light, but they always follow straight path of light. So what I've drawn here is a simple diagram wherein I have shown a container with water, and we have placed a coin inside the container here. And let's assume that there are two light rays which are starting from the coin and moving out of the water. So one is going straight up, perpendicular to the water surface, and one is traveling in this particular direction after diffraction. Note that the light ray traveling perpendicular to water surface will not bend. This is one situation under which light rays will not bend if it is entering from one medium to another perpendicular to the refracting surface. Now, let's assume that someone is looking at this coin from this particular angle. So these light rays will reach his eyes, but since our eyes are trained to follow only straight path of light, our eyes don't follow bent path of light. So the eye will follow straight path of light, which will be something like this, and hence the coin will be seen here rather than its actual position. So this is the actual coin, and this is where the person will be able to see the coin, which is higher than the actual position of the coin. So this happens because of refraction or bending of light. So what is the real reason behind bending of light as it passes from one medium to another? The simple reason is when light passes from one medium to another having different densities, the velocity of light will change. And whenever the velocity of the light changes, it is going to bend either towards the normal or away from the normal. For example, when the light ray enters from air to glass, the velocity decreases, so it bends towards the normal. Or when it moves from glass to air, the velocity increases, so it bends away from the normal. There are only two conditions in which light rays can pass straight without bending from one medium to another. The first condition is when the light ray passes perpendicular from one medium to another, or if density of both the media is same. In that case as well, the light ray will pass straight without bending. Now remember, when I say density here, I'm talking about optical density. Optical density is slightly different as mass density, which you've learned in standard 9. Mass density is mass per unit volume. Let's take an example to understand this. Suppose I pour kerosene in water. Now we know that kerosene has less mass density, so the kerosene will float. So here it is proved that kerosene is lighter than water because of the less or lower mass density, whereas water has higher mass density, so water will actually sink at the bottom. But if I pass light through both these media, I'll find that the light travels faster in water as compared to kerosene. So that means kerosene has higher optical density as compared to water, but lower mass density. Now this optical density can be also called as refractive index, which we'll see in the later part of the chapter. So just remember, mass density and optical density are not exactly the same. Let's understand refraction with the help of this very simple experiment. So in this particular experiment, we have a glass slab here, and let's name it as something like ABCD. And let's assume that a ray of light is passing from air into glass. So as we have seen in mirrors, or as we have seen in reflection of light, a light ray traveling through air and hitting the surface of the glass slab here will be called as incident ray, just like we saw it in mirrors. Now we have drawn a normal here, as you can see, which is perpendicular to surface AB, and this normal is making an angle with this incident ray, and like we have seen in mirrors, we'll call this as angle of incidence. Now this light ray at this particular point is entering from air to glass. Now air is a rarer medium, means air has lesser density as compared to the glass. So glass is comparatively a denser medium. So when a light ray passes from rarer medium to denser medium, it will not pass straight because the density is different. So as you can see, I have shown with dotted lines that this is the original path of this particular light ray. But because it is passing from denser to rarer medium, this light ray will bend towards the normal, or it will bend closer to normal, forming an angle with the normal, and this angle will be called as angle of refraction. So remember, whenever a light ray passes from rarer medium to denser medium, it bends closer to the normal instead of passing straight through because of the change in density. Now this light ray continues to travel through the glass and ultimately reaches the surface CD. At CD, this light ray is now entering from glass into air. So it is coming from a denser medium to rarer medium now. In this case, a reverse thing is going to happen. That means you'll find that this time the light ray, again, it will not travel in a straight line, but if I draw a straight line path of this light ray, it's going to be something like this. But it is not traveling in a straight line, it is bending away from the normal this time. So here, by the way, we'll get angle of incidence here, and it forms another angle here with this particular normal. We call this as angle of emergence. So remember, whenever a light ray passes from denser medium to rarer medium, it bends away from the normal. So let me just repeat what we have seen so far. We are assuming that a light ray is entering from air to glass. Air is a rarer medium, glass is a denser medium. This light ray hits the surface AB of the glass at point O. So this point is called point of incidence, and this light ray here is called as the incident ray. We can name it as something like PO. Now it forms angle with the normal, and this angle is called as angle of incidence. Then once it enters the glass, instead of traveling in a straight line, it bends and enters into the glass, and it bends towards the normal. So as I told earlier, you have to remember that whenever a light ray passes from rarer medium to denser medium, it is going to bend closer to the normal. So it forms an angle with the normal. This is angle of refraction. Then it hits surface DC of the glass and forms another angle of incidence here. And you will see that this time it is moving from denser medium to rarer medium. So it is going to bend away from the normal, and we call this angle as angle of emergence. It has been marked wrong here. So this is angle of emergence. The angle formed by emergent ray with the normal is called as angle of emergence. You would have noticed one more thing here, that the path of incident ray, which is this path shown by dotted line, is parallel to the emergent ray. So again the question arises, why is the path of incident ray parallel to that of the emergent ray? Now the reason for this is the refraction happening at AB is equal and opposite to the refraction happening at CD. In other words, let's say if the angle of incidence at AB was say 35 degrees, just for our understanding, and angle of refraction was 15 degrees, then at CD, angle of incidence will be 15 degrees and angle of refraction or emergence is going to be 35 degrees. So the amount of refraction happening at AB is equal and opposite to CD, and hence you will see the lateral displacement, and hence the emergent ray is parallel to the incident ray. So that was the basics of refraction of light. There are two important laws of refraction which you need to remember. One law says that the incident ray, the refracted ray, and the normal to the point of incidence, they all lie in a same plane. So you are familiar with this kind of a law we have seen in reflection of light. It's basically very similar. Only thing we change one word here, that is the refracted ray of light. The second law which you need to remember is called as the Snell's law of refraction. As per Snell's law of refraction, the sine of angle of incidence to the sine of angle of refraction is constant for given color of light and given pair of media. So this particular law is called as Snell's law of refraction. So these are the two laws which you need to remember when it comes to laws of refraction. In the Snell's law, we saw that sin I, or sine of angle of incidence, to the sine of angle of refraction is constant for a given color of light and given pair of media. This particular constant is called as the refractive index. Refractive index is given by letter N. Now, since refractive index is a ratio, it does not have any unit, it will just have a value. Now, how do we calculate refractive index? First of all, we should know there are two kinds of refractive indices. One type is called as the absolute refractive index, and the other type is called as the relative refractive index. So let's understand the difference between the two. They are not much different, but let's understand what it is. When I say absolute refractive index, it simply means I'm comparing the speed of light in a particular medium with respect to air or vacuum. So if I want to write the formula for calculating the refractive index of glass, if a light ray is passing from air to glass, in this case I'll say refractive index is equal to C, which is the speed of light in air or vacuum, divided by V, which is the speed of light in glass, and this will be your speed of light in vacuum. So if I divide these two values, I'll get the value for the refractive index of glass. Now here I'm comparing the speed of light in glass with respect to vacuum, so we'll call it as absolute refractive index. The other type of refractive index is called the relative refractive index. Now let's change the example a bit. Let's say the light ray is passing from water to glass. Now here you can note there is no vacuum or air, there is water and glass. So again I want to find the refractive index of glass. So this time my formula would be refractive index of medium 2, which is glass, with respect to medium 1, which is water, will be equal to speed of light in water divided by speed of light in glass. Now this is called as relative refractive index because I am comparing the speed of light in glass with speed of light in water. I am not comparing it with the standard, that is vacuum. So this is relative refractive index. In either case, what does the value of refractive index tells us? Refractive index value tells us how slow the light ray is traveling in a particular medium as compared to some other medium. For example, let's say I find refractive index of a particular material, absolute refractive index I mean, of a particular material as 2. So I can say that the light is traveling 2 times slower in this particular medium as compared to vacuum. I'll repeat again. We have assumed that the refractive index of a particular medium X, let's say, is 2. What is the meaning of this? It simply tells us that light is traveling 2 times slower in the medium X as compared to vacuum. If I apply the same logic in, let's say, relative refractive index, let's say the light ray again is traveling from water to glass or water to medium X, and I again find the refractive index of medium X as 2 here, I would say the same thing, that the light is traveling 2 times slower in medium X as compared to water. So this is what the refractive index is all about. You need to remember one more thing though, one more logic. The higher the value of refractive index, the higher will be the density of that particular medium. This will be very important while solving some questions. The next part that we have to see is spherical lenses, and there are 2 types of spherical lenses that we are going to learn. One is the convex lens, as you can see here, whose refracting surface is curved outwards like this, and the second lens is called the concave lens, which is like an sort of like an hourglass shaped, whose refracting surface is curved inwards. Now remember that the convex lens is the converging lens and concave lens is a diverging lens, which is exactly opposite to mirror, where concave is converging mirror and convex is diverging mirror. Here it is opposite. So let's understand the different points that we need to remember with respect to these lenses. Alright, so let's understand the different points that we have to remember with respect to lenses, just like we did in the mirrors. Now if you have not seen that video, please go and watch that video. I'll link the video in the description below. This lens, the lens which I have shown on the top, is your convex lens. whereas the lens below, which is like an hourglass shaped, as I said earlier, is your concave lens. Okay. The center of the reflecting surface of the lenses is given by letter O, and it's called as optical center. Center of the reflecting surface of the lens given by letter O, called as optical center. Now, as you can see, the lenses have two spherical surfaces, and the dotted lines which I have shown here, they are basically we are assuming that these curved surfaces have come from these spheres. So these spheres have centers. This is the center of this sphere. This is the center of the first sphere. So we can name them as C1 and C2 as they are centers of curvatures of these spheres. But we can also name them as 2F1 and 2F2. Likewise, here also there are two centers for both the spheres. We can name them as 2F1 and 2F2. An imaginary line joining all these 3 points can be called as the principal axis. So most of the things are very similar to that we have seen in mirrors, but in mirrors there is one focus and one center of curvature. Here we'll find two foci and two center of curvatures and all that. So it's just double because there are two spherical surfaces. Now, the convex lens is a converging lens, which means, so let me write that here, converging lens. Which means, if I pass light rays parallel to the principal axis of this lens, then these light rays will actually meet at a point or converge at a point on the principal axis. This point where they converge or meet is called as focus, given by F. But since the lenses have two spherical surfaces, I can pass light rays from the other side as well. And if I do so, I will get one more focus at a point where the light rays will converge or meet. So that means you've got two foci, and we can name them as F1 and F2. So basically, I'm getting 5 different points here. Let me draw that more clearly here. The first point that we saw was optical center, which is basically the center of the refracting surface of the lens. Then we saw two centers of the spheres, which we named as 2F1 and 2F2. And wherever the light rays are converging, we got two more points between O and center of curvature, and these were named as F1 and F2. We'll see the same thing in concave lens, but concave lens is diverging. These are diverging lens, which means if I pass light rays parallel to the principal axis of this lens, then these light rays will diverge in such a way that they will actually appear to diverge from a point on the principal axis. And the point from where they appear to diverge is called the focus of concave lens. So convex lens has real focus where the light rays actually meet or converge, whereas concave lens has virtual focus. Similar to convex lens, if I pass light rays from the other side, if I pass light rays from this side, I'll get one more point here, one more foci. So we can name it as F1 and F2. So these are the different points we need to remember about concave and convex lens. So just to be clear, this diagram also shows you the different points of convex lens, and concave lens also, as you know, has similar points. So you can see I have mentioned here, this is the optical center, which is the center of the refracting surface. These are the two foci where the light rays will actually converge or meet after refraction, and these are the center of curvatures of the sphere. The next part that we need to see is image formation by convex lens. Now, just like mirrors, here also we need to follow certain rules. So first let's have a look at the rules, and then we will proceed with the diagrams. So let's see what are the rules that we need to follow to draw the diagram for the image formation in convex lens. There are three simple rules here. The first rule says that if a light ray is traveling parallel to principal axis, after refraction, this light ray will pass through focus. Remember, lenses refract light, they bend light, they don't reflect light like mirrors. So that is your first rule. Second rule says that if a light ray is passing through focus before refraction, then after refraction, it will travel parallel to the principal axis. That's the second rule. Third rule is even simple. Third rule says that if a light ray is passing through the optical center, it will pass straight without any deflection or without any refraction. So these are the three rules for drawing the diagram. Out of these, we can use any two rules and draw the diagram, just like we did in the mirror. So let's see how we draw ray diagrams of convex lens. So let's see how a convex lens forms image by placing the object maybe between f1 and 2f1. So what I've done here is I have drawn the principal axis, horizontal line, and then I have marked 5 points at a distance of 2 centimeters or 3 centimeters would be also fine. The thing is that they should be at equal distance from each other. So the first point, as you can see here, is 2f1, then comes f1, then comes O, this is the third point, then comes f2, the fourth point, and then comes 2f2, which is the fifth point. Then on both the sides of optical center, I have marked 2 more points. These are the markers from where we are going to draw the arcs for the lens. So basically you can take these points at half a centimeter on both sides of O, half a centimeter left hand side, half a centimeter right hand side, or even 1 centimeter would do. So if you are using a compass to draw the lens, hold your pointer at 2f1 and then extend it up to this particular point on the right hand side of optical center, and then you are going to mark an arc on that point with your compass, like so, more or less. Likewise, you will go to 2f2 and come to this particular point on the principal axis on the left side of the O, and from there you are going to mark an arc with your compass something like this. So now we have got our lens. We'll remove any excess part of the lens, and then if needed we can also draw a dotted vertical line passing through the optical center. Now this is a guiding line which will tell us that from this line the diffraction is going to happen. This is just a guiding line. It's optional. If you don't want to draw it, it's okay. Now let's say we'll place the object between f1 and 2f1. Now the position of the object will be given in the question. You will not have to worry about that. We'll name the object as AB. Now let's follow any of the two rules and try to find the position of the image when I place the object between these 2 points. So let's use the first rule first. The first rule says that if a light ray is traveling, if a light ray is traveling parallel to principal axis, after refraction it will pass through focus. So this is going to be my first rule or first light ray. Now let's draw one more rule. Maybe I'll use the third rule because third rule is easier to draw. You have to just draw a straight line passing through the optical center. This lens. And when I do this, you can see I'm getting an intersection which is beyond 2f2. So wherever I get the intersection, I'll draw my image at that particular point. Let's name the image. Let's call it as A1B1. So as you can see, I'm getting a real image here, which means there is an actual intersection of light rays happening. The position of the image is beyond 2f2, and the size, if you compare it with the size of the object, so this is the size of your image and this is the size of the object, it is definitely an enlarged image. So this is how you draw ray diagram for convex lens. Let's take one more example for convex lens. So let's try another diagram wherein I have placed the object between f1 and the optical center. Now I have drawn all the points and lengths which is required for this. Now let's just simply follow the rules and see what we get. So the first rule says that if a light ray is traveling parallel to principal axis, after refraction, it will pass through focus. That's one rule. Now, second rule, or we are really good to use the third rule. Let's see what happens when we draw the third rule. You can see that when we draw these rules, we are getting diverging light rays. So one light ray is traveling in this direction, the other light ray is traveling in this direction. So we're getting diverging light rays. When we get diverging light rays like this, we will just simply extend these light rays behind or backwards and see if they appear to meet. Remember, we have to just extend the same light rays with dotted lines behind and see if they appear to meet at any particular point. So I'm drawing the second light ray now and extending the second light ray rather, and you can see that these light rays appear to meet at a point on the principal axis. So this is the point where your image is formed. Now, obviously, since the light rays are not actually intersecting, this is a virtual image formed by the convex lens. So this particular diagram is very important in the sense this diagram explains why convex lens can be used as a magnifying lens. So when you place the object between these 2 points F1 and O, you get a magnified image of that object, virtual, erect and magnified image of that object, which is what makes it useful as a magnifying lens. Also, you must have seen watchmakers or watch repairers use a tiny lens in front of their eye to see the magnified image of the tiny parts of the watches. Basically, it is the same lens and same concept can be applied there. That is, when the object is placed between F1 and O, we get magnified image of that particular object. Let's move on to concave lens. Let's understand the rule for drawing the concave lens diagrams. So the first rule says that if a light ray is traveling parallel to principal axis, it will diverge in such a way that it will appear as if it is diverging from F1. That's the first rule. Second rule, if a light ray is traveling or passing through optical center, it passes straight without diverging. And third rule is kind of opposite to first one, not very important for us for drawing images, but let's see. Third rule says that if a light ray appears to pass through focus, then after refraction it will travel parallel to the principal axis. So these are the three rules, but we mostly use rule number 1 and rule number 2, which I've shown here. So there are really only two diagrams for concave lens. One is when the object is placed at infinity, which I'll show you in a minute what happens when the object is placed at infinity. The second diagram is when the object is placed between infinity and optical center, so anywhere on the principal axis literally. So wherever you place the object on the principal axis, you are going to get the same result which I have got here. Wherever you place the object on the principal axis and draw these two light rays, you are going to get image formation between F1 and O, which will be virtual, erect and highly diminished. So remember, concave lens being diverging lens, it is always going to produce a virtual and erect image, and it will be always diminished. In this case, when you place the object between infinity and pole, it will be always between F1 and O. And if you place the object at infinity, it will be formed at the focus. So these are the two diagrams I was talking about, that if I place an object outside the principal axis, that is at infinity of a concave lens, the light rays traveling parallel to the principal axis from the object will appear to diverge from the focus and the image of this object will be formed at focus. This image will be highly diminished and point-sized, but it will be still virtual because the light rays appear to diverge from that point. On the other hand, if I place the object at infinity of a convex lens, again it is going to form a highly diminished image at focus of the convex lens, but this will be a real image as the light rays are actually intersecting. So suppose I focus the light rays of the sun by using a convex lens and keep a paper at the point of focus here. It will cause so much intense heating that the paper will start burning after some time. The next part of this chapter is numerical problems. Now these problems are really similar to the mirror problems, and we use same sign convention that we used in the mirror problems. So if you have not seen that part, and if you want to understand the sign convention of what is to be taken negative and what is to be taken positive, please watch the part 1 of this chapter, that is reflection of light. As I said, I'll leave a link below in the description. Now the only thing that changes here with respect to sign convention is the value, the sign of V. V is image distance. In lenses, the virtual and erect images are formed on the left hand side of the lens. That means V for virtual erect images becomes negative, and real and inverted image are formed on the right hand side, which means V for real and inverted image becomes positive, which is exactly opposite to mirrors. All the other sign conventions, including the focal length of concave mirror is negative, focal length of concave lens is also negative, focal length of convex mirror is positive, focal length of convex lens is also positive. So all the other sign conventions remain exactly the same, only V is opposite. In mirrors, for real and inverted images, V is negative, in lenses it is positive, and for virtual erect image in mirrors, V is positive, in lens it is negative. The lens formula also is very similar to the mirror formula. So the lens formula is 1 upon V minus 1 upon U. The sign changes here. Minus 1 upon U is equal to 1 upon F, where V is the image distance, U is the object distance, and F is the focal length, same like mirrors. Magnification formula is also similar, only the sign changes. So M is equal to height of the image, which is HI, upon height of the object, which is equal to V upon U instead of negative V upon U. So formulas are almost similar, only thing that changes is the sign. So let's solve a problem. So here is a problem. Let's decode this problem first, like we have done in mirrors, and then we'll try to understand how to solve this particular problem. So the first statement says a 5 cm tall object is placed perpendicular to the principal axis of a convex lens of focal length 15 cm. So we understand that the lens here is convex lens. So let me draw a rough diagram. So I'll draw a convex lens here. This is the principal axis or the x-axis. This is the y-axis. Now, just like mirrors, you have to assume that the optical center of the lens is at 0, 0, which is here. Now, since we place the object on the left hand side, U is always taken negative, like we have seen in mirrors. The height of this object is given, which is measured vertically upwards. This is your height of the object, which is 5 centimeters. So first thing that is given to us is HO is equal to positive 5 centimeters. Focal length is given as 15 centimeters in the problem. So we consider the focus on the other side of the lens, because the object is placed on the left hand side, this distance between the optical center and the focus is called as focal length, given by small f. So here focal length of the convex lens becomes positive, so again plus 15 centimeters. The distance of the object from the lens is given as 20 centimeters. That means this distance from the optical center to the object is u, which is given as 20 centimeters. Remember, u is always negative, so u will be negative 20 centimeters. We have to find the height of the image and the distance of the image, which means we need to find what is v, which is the distance of the image from the optical center, and we have to find height of the image or the size of the image. We can also find magnification if you want, but this is what we need to find for now. So let's write the lens formula: 1 upon v minus 1 upon u is equal to 1 upon f. Let's shuffle around the formula. 1 upon v is equal to 1 upon f plus 1 upon u. Let's substitute the values. F is 15, so 1 upon 15 plus 1 upon negative 20. Now the LCM of 15 and 20 is 60. So I'll get 15 multiplied by 4 is 60. Negative sign as it is. 20 into 3 is 60. Therefore, I get 1 upon V as 1 upon 60. Reciprocal on both the sides, V is equal to 60 centimeters. So the image is formed 60 centimeters on the right hand side. Now how do I know it is on the right hand side? Because here the value of V is positive. So I know that the image is formed at 60 centimeters on the right hand side of the lens. So next thing we need to find is height of the image. The formula that we need to use is height of the image to the height of the object is equal to V upon U. Now height of the image we need to find. Height of the object is given to us, that is 5, is equal to V is 60 as we have just found out, and U is negative 20. So I'll cancel. 21s are 20, 23s are 60. If I cross multiply, height of the image comes to, since there is negative sign left, I'll get negative 15 centimeters. The negative sign on the height of the image shows that the image is real and inverted. Real and inverted. And we also know, if we compare with the size of the object, the image is enlarged. Since the size of the object is 5 centimeters and the size or the height of the image is 15 centimeters, this image is enlarged. The last part of this chapter is power of lens. By definition, power of lens is said to be reciprocal of its focal length in meters. So P is equal to 1 upon F. Remember, where focal length has to be strictly in meters. So in other words, the power of lens is said to be 1 diopter if focal length is 1 meters. So this relation is very important to remember. Just like the focal length of the lens is taken as negative and positive, power of lens also is taken as negative and positive. For example, power of convex lens will be taken as positive, whereas the power of concave lens is taken as negative. Unit of power is diopter. As I said, 1 diopter is a power of lens with 1 meter of focal length. So unit of power is 1 diopter. Another definition which we can give is power is said to be degree of convergence or divergence brought about by the lens. That could be another definition, but you can also write it as reciprocal of its focal length in meters. So P is equal to 1 upon F. So what exactly is the meaning of all these technicalities that we saw just now? Let's understand this with an example. Let's say I have 2 lenses here, lens A and lens B, both are convex lenses, and I have drawn light rays parallel to the principal axis of these lenses. Lens A converges these light rays at this particular point, which is obviously the focus of this lens, and lens B converges at this particular point, which is the focus of lens B. Let me also mark the optical centers of both these lenses. Now, if you compare the bending of light rays happening in these 2 lenses, you will see that lens A is bending the light rays lesser as compared to lens B, and hence the light rays are meeting farther away from the optical center in lens A as compared to lens B, which also means lens A has longer focal length because this is distance between O and F is focal length, whereas lens B has shorter focal length. Now remember that as per the formula, P is equal to 1 upon F. Power and focus has inverse relation, which means greater the power of the lens, shorter will be its focal length. Now out of these 2, lens B has shorter focal length. So we can say that lens B has greater power, whereas lens A has longer focal length, so lens A has lesser power. In other words, whichever lens bends the light rays more has more power, and whichever lens bends the light rays less has less power. That's why we wrote another definition, as you saw, that degree of convergence or divergence brought about by the lens is called power of lens. Now let's solve a problem on power of lens. So let's solve this very simple problem, which will be the last part of this particular chapter. So the problem says, calculate the power of a diverging lens whose focal length is 25 centimeters. So let's see how to do this. It's very simple actually. The formula that we are going to use is P is equal to 1 upon F. Now, we already know that power of a lens is said to be 1 diopter if the focal length of the lens is 1 meter. But in the problem, focal length has been given in centimeters, so we'll need to convert it to meters. And as you know, if I divide 25 by 100, I'll get 0.25. So I'll say P is equal to 1 upon 0.25. Now I have to also take a negative sign here, as I have said calculate the power of a diverging lens. Remember that focal length of a concave lens is taken as negative. So if I calculate, I'll get the answer to this as negative 4 diopters. So that would be my answer. Now if you are confused with decimals, or if you want to remove the decimals and then divide, you can simply multiply both numerator and denominator by 100. So I will get 100 upon negative 25, and that's how I get the answer as -4 diopters. So that's how we can solve simple power problems. Sometimes in the lens problems, they will not directly give you the focal length, but they will give you the power of the lens and ask you to find the focal length. But you can use this formula and easily find the focal length and then use it in the lens problem. So that is the end of refraction of light. If you have not seen the first part of this chapter, reflection, I have already uploaded a video on reflection of light. Please do go and watch it to get your concepts clear on the reflection of light. I'll also leave a link below in the description. Also, please don't forget to subscribe the channel. It will help me grow. As always, thank you for watching. See you in the next one.